Hello, and welcome back to another episode of South Pole, the podcast that explores everything Antarctica. I am your host, Clark Marchese, and today we are about to embark on a journey to the past. No, we are not talking about Anastasia and the Romanovs. We are talking about paleoclimatology, ice cores, and the oldest Earth system records we have. All right, today on South Pole, we have another ice word, ice cores today, which we will learn are time capsules of sorts. Joining us is Dr. Tas van Ommen, a renowned Antarctic climate scientist and adjunct professor at the University of Tasmania. Dr. van Ommen has been at the forefront of ice core research for over 30 years, participating in multiple expeditions to Antarctica to drill ice cores, which contain vital information about our planet's past climate. In the episode, we'll discuss what exactly ice cores are, what types of data about our planet's past climate that they store, what they can tell us about how our Earth systems operated in the past, and how they might change in the future. We'll also talk about how this knowledge can even inform our current environmental mitigation policies, particularly how information from ice cores is actually helping us address droughts in Australia. And believe it or not, some of these ice cores are over 4 kilometers long, so we'll also hear about what it's actually like to harvest them. Now, without further ado, let's dive a couple kilometers below the surface of Antarctica and welcome Dr. Tas van Ommen to the show. All right, we are recording. Good morning. Thank you for coming on today. The first question I have is if you could just introduce yourself and tell us a bit about your research.
Sure. My name's Tas van Ommen. I'm an Antarctic climate scientist. I've worked in the field for probably close to 30 years, working mostly for government, although these days I'm an adjunct professor with the University of Tasmania in Hobart.
Okay, so one question I'm asking everyone, and I'm sure you get this question a lot, but have you ever been to Antarctica? And if so, can you tell us about some of the projects that took you down there?
Sure. I've been on 6 research expeditions to Antarctica, mostly drilling ice cores, which is my specialty, and I'm sure we'll be talking more about that today. But using ice cores to understand past climate, so those trips typically took me away for somewhere between 2 weeks and maybe 8 to 10 weeks over the summer in Antarctica, which is when you can get out and do that kind of work. And I've also been involved in trying to understand how Antarctica is structured, about the bedrock underneath. And for that work, I've been flying over Antarctica in a specially equipped plane where we map the bedrock underneath. So that's kind of a different view on the continent from boots on the snow, but still really exciting work.
Okay, that sounds quite adventurous. I want to get some more details about that in a minute, but one of the terms that I've seen attached to your work is paleoclimatology. Is this the work of a paleoclimatologist? Can you tell us what a paleoclimatologist does?
Yeah, we very quickly learn that when we're describing our work to the lay people or politicians or policymakers, past climate's probably a better way of describing it. But paleo just means old or ancient. And so what we do, we're part of a significant community of Earth scientists who try to understand the Earth's climate by looking at how it's behaved in the past. Because, if we look at it these days, we've had nice instruments, satellites for 30 or 40 years, thermometers and pressure gauges for maybe a couple of 100 years. We really don't have a way of looking at the long-term behaviour of the climate system without using some clues that get stored away in the Earth. And those clues, that's the field of paleoclimate. Ancient climate, might come from tree rings. People often sort of understand intuitively, cut off a tree and see those rings and they tell you something about past climate. Ice cores do, and we'll talk more about that. Coral also has growth rings. There are layers of mud and silt in the bottom of the ocean or in lakes. All of those tell us things about past or paleoclimate, and that's how we figure out the way the system works.
Okay, that's super interesting. And you also just answered another question that popped into my head, which was I know that you focus on ice cores, but I was wondering what other sorts of, I guess, research objects, for lack of a better term, that can give us information about the past climate. But it seems like you can find information from lots of different things. But on South Pole, ice cores is what we're going to be talking about today. And we've covered a couple of Antarctic ice words so far. To set the stage for the rest of the conversation, maybe can you just tell us what an ice core is?
Absolutely. So in places like Antarctica, but also other really cold places like on the tops of really high mountains or in Greenland, the snow that falls each year doesn't melt away in summertime, at least not completely. And so every year you end up with a layer of ice or snow to begin with that gets buried by the next year, and that gets buried by the next year. And so you can think of the ice sheet, we tend to call it the ice sheet, but the ice caps too on the mountains, glaciers, as being made up of these layers year upon year upon year of snowflakes that get compressed by the weight of the next year's layers. And in fact, over my shoulder, the background image I've chosen is the edge of Antarctica. It's where the ice meets the ocean, and you can see that as the ice breaks off, all of these fantastic layers down through the ice, which show you the annual layers. Now, eventually, those layers get squashed down to solid ice. And also, because the ice is flowing off of Antarctica very slowly, it's kind of stretching out like dough in a bread or something, a stretching bread dough out. And that squashes the layers even more. And so by the time you get to the bottom of really thick ice, might be 3 or 4 kilometres thick in the centre of Antarctica, those annual layers are down to, microscopic size. And so you can get hundreds and hundreds of thousands of these layers stored away in the ice.
Wow, 4 kilometers of microscopic layers. So would one layer equal one winter season, or is it a bit more complicated than that?
It really depends. I mean, if you look at the ice once it's turned to solid ice, the eye doesn't really detect layers at all. But what you can see is that if you measure the chemicals that get stored away, I mean, a classic one is every winter you get, especially at the coast, these massive storms that happen around Antarctica, and they blow in salt spray in small quantities, but you can still measure that salt. And so if you measure the chemicals in the ice, you typically see every winter has got this saltier layer than the summers, which are calmer. And that applies to nearly everything you measure. There's a seasonal change. And so when you want to actually get that information, you've got to get that ice out somehow. And that's where the ice coring itself comes in. So we go out on the ice with a special drill that's hollow down the middle. It's kind of like a donut ring, a pipe, if you like, and you spin that as you go down into the ice, and that actually cuts out a cylinder of ice that you can bring back to the surface and get those really old layers.
Okay, wow, it's almost like a biopsy of the ice. How do you actually go about doing that kind of work? Can you paint a picture for us?
It's a pretty exciting process, actually. I mean, it's been the highlight of my career to get into the field and actually do the work. It's fun to get back to the lab and think it through as well. But drilling a core typically for us involves, if you can fly sometimes, if you're doing a small lightweight expedition, but typically we have to get on tractors and travel over the continent for days. In fact, the longest trip I did took me 2 weeks of travelling 10 kilometres an hour every day in a tractor train. And then when you get there, you're 1,000 kilometres from the nearest human settlement. You've got to look after yourself and get sort of all of those activities that just to survive in a place that basically wants to kill you. I mean, it's really cold, minus 40 degrees, and living in tents. But in the midst of all that, then you've got the equipment you take with you. Ice core drilling is really intensive exercise because I've said a little bit about it, but you lower this spinning drill into the ice. It hangs on a cable, right? And you can only drill for about 2 or 3 metres at a time before you then have a full drill barrel, and you have to pull the cable back up, take the ice core out, and then repeat the process. So in a typical summer season, we might be able to do, with a lightweight drill, 300 to 400, 500 metres if you're very lucky of ice core. And there's all the challenge that goes with then handling it as cleanly as possible, packing it up, keeping it frozen in transport, flying it or shipping it back to the labs here in Australia or overseas. And that's exciting too, because there's no one lab that can analyse for everything. So you end up, cutting up your core into many pieces that you end up sending to labs all over the world to help get your analysis done. But in the field, it's just magical. It's a fantastic experience and very rewarding. And you have to solve things yourself. I mean, we like to say here that the local hardware store is not just down the road. If it breaks, you fix it or your season's over.
That seems pretty intense, but it also makes total sense that you chop the ice up into chunks. I was literally picturing like a 4-kilometer long cylinder of ice, being transported and then analyzed in the lab, but that does not make much sense, I guess. But anyways, this is kind of a big question, so we can tackle it in chunks if we need to. But it is, what sorts of things can ice cores tell us about the past? You mentioned that we look for salt. You also mentioned that it can tell us about some chemicals that used to be in the climate or are in the climate. So what sorts of things are stored in the ice? What are we looking for? And I guess, how does that translate to meaning about the climate at any given time?
A really good question. So the salt is just one of the things that I used as an example, but there's kind of three main types of things that you measure in the ice. The first is chemicals like salt, like dust that gets blown in from distant continents, and like sulfur that gets deposited when a big volcano goes off. That sulfur gets up high in the atmosphere and gets blown down and eventually settles on Antarctica. So that's one kind of thing. All these chemicals are one of the things you find, and each one of them tells us something different that I can come back to. The second broad type of information you get out of the ice is really cool, and that is that between the snowflakes, as they settle down together and pack down, they trap air from the atmosphere. And so that trapped air in the atmosphere, actually by the time the ice or the snow gets compressed into solid ice, you end up with tiny bubbles trapped in the ice. And those air bubbles are bubbles of ancient air. So what you get out when you've got a piece of ice that might be 500,000 years old, you can actually then take the bubbles in that ice, crack them open, and analyse what the atmosphere was like 500,000 years ago. Say, for instance, want to know what carbon dioxide was doing before we started messing with the atmosphere? That's the direct way you can do it. And it's really cool because it's a direct measurement. We're not guessing what the atmosphere did to something else. We're actually measuring true little time capsules. So that's the second type. And the third type of information we get out of the ice is actually from the water itself. Even if there were no bubbles, no chemicals, the water is made up of H2O, hydrogen and oxygen. And like most elements on Earth, these oxygen and hydrogen atoms have different weights of elements, isotopes we call them. So there are heavy variations of oxygen and there are heavier variations of hydrogen. And they actually get transported to Antarctica a little bit differently than the lighter ones. So to cut to the chase, by analysing these isotopes of hydrogen or oxygen, we can figure out what the temperature was when the ice or when the snow fell. So that's the third type.
Okay, so we've got earth, wind, and fire. No, wait, sorry. We've got chemicals, air, and water.
And so putting that all together, and we can talk about individual chemicals in a minute, but what ice cores give us is possibly the most valuable past climate information you can get, because they tell us about the things that force the climate, like volcanoes, like carbon dioxide, like even the sun's activity, and I'll tell you how that works in ice. So we know about the things that force the climate, and then we can look at how the climate responded as well by the temperature changes and by the way winds change and that sort of thing. So if you like, the ice cores are a recorder of the drivers and the responses of climate. That's cool.
I feel like some dots were just connected for me in a sense, because I think I kind of surmised that you could identify the drivers, but being able to identify the responses as well, that's kind of like the full piece of the puzzle. I was going to ask you about volcanoes actually, because I came across a bit of that in some of your research that you can tell, for example, when a volcano erupted. And then my question was going to be, so why is it important to know that? But I guess volcanic activity can be a driver of climate changes.
That's right. Yeah, and look, it's a really nice natural experiment because when a volcano goes off, it actually gives the climate system a temporary kick. You get all of that sulfur that gets thrown up into the high atmosphere and causes clouds, which you might have seen after a volcanic eruption for a year or so. You end up with these spectacular sunsets that reflects extra sunlight back to space. And so you are able to start to conclude, how did the Earth's temperature change when the volcanic eruption was really big? Or how did it respond when the eruption was kind of smaller? And so for that kind of work, you want just not one ice core. You want as many ice cores as you can get from both the Northern Hemisphere, which is usually Greenland, and Antarctica. And you build up almost a chronology or an atlas of past volcanic eruptions. So that's a really good example. The other thing I mentioned we can get is information on how the sun has varied in the past. And that's really cool because one of the first questions people ask when they start to really understand climate is, well, so it's warming up now. How do we know that's not the sun just changing the climate? Well, the ice cores tell us. We know what the sun did in the past because when the sun actually affects the Earth, it actually shields us with its magnetic field from really powerful cosmic rays that come from space. And so you get a pattern where when the sun's strong and putting out more sunlight, just a little bit, a few percent or less, you end up blocking off some of these cosmic rays that hit the Earth's atmosphere. And that changes the amount of carbon-14 that gets produced. You've probably heard about carbon-14 because that's used to date old things that are organic. We measure something that's kind of related to carbon-14. It's called beryllium-10. And so, again, to cut to the chase, the variations in the beryllium-10 actually allow us to understand how the sun has varied in its activity over the past and gives us a really good handle on the solar forcing of the climate.
So it's not the sun causing our problems, it's just us. My next question is, once we have collected all of this data from the past and sort of gained an understanding of how these things used to be, is there a way to use this data to either project how the climate will change in the future or how our Earth systems will respond to any changes that might occur?
Really good question. And really, you're getting to the heart of what drives paleoclimate. We look at the past not just because we're curious about the past. I mean, that would get a bit stuffy for most of us after a while. We look at the past because we want to understand how the system works, because we need to understand what's going to happen in the future. Now, when it comes to the climate, we've got a lot of ways to understand it. We've got our understanding of physics. We know how radiation penetrates the atmosphere. We understand how clouds are formed, and we can model and actually predict weather quite well compared with, say, 20 or 30 or 40 years ago. And for predicting climate, it's essentially the same set of equations, but we're not concerned about the day-to-day and month-to-month variations. We're concerned about the drivers and trends. But getting back to paleoclimate, if all you had to test your climate models was just the weather records of the last 30, 50, 100 years, not much more, you couldn't be super confident that your climate model is capturing things that change the climate on longer timescales. I mean, for example, we know that ice ages come and go. Ice ages are typically on, tens to hundreds of thousands of years to repeat themselves. But how do we know there's not something missing from our climate models if all we had was the modern instrument record? And the way we know is that we can actually use climate models to test against the observed paleoclimate record. And what we find, for the most part, is that the models can reproduce a lot of what we see in the climate record. And where they differ, that's become a clue for us to be able to go back and say, I think the models are missing some kind of process, quite often to do with the way longer-term ocean circulation varies and interacts with the atmosphere, or perhaps to do with the way ice sheets grow and decay. All of that information we can get from looking at past climate. And so the way we understand the future isn't so much just the past climate itself, it's the models that we now are confident have been tested against our knowledge. Does that make sense?
I think I followed. So we're referencing this record of the past to sort of check the accuracy of the climate models we come up with today. But that did make me think of another question based off of, I guess, the patterns that we see in these records. I know that we've had a couple of ice ages that, come and go somewhat cyclically, but then I was also thinking about a volcano eruption, which I was just about to say are random events, but as I'm speaking, I'm sure volcano scientists, roughly know when they might happen. But in any case, I don't know if they're as cyclical as ice ages. So my question is, when we look at the ice record, are we able to identify what is a long-standing pattern versus what is an anomaly?
That's a really good question. And one of the things that we do with the paleoclimate record is we look for cyclicity, for patterns and for various. One of the reasons we want to do that is if we're seeing changes now, we want to know to what extent those changes are just part of what we call natural variability and where they're not natural variability. So a really good example is the increase in global temperature we're seeing now. Is that unprecedented or is it something we've seen in the past? And actually, that's a really good example because if we put together all of our information from paleoclimate, from tree rings and ocean sediments and everything we've got and ice cores, we can now reconstruct the climate of the last 10, 15, 20,000 years quite well globally. And what we see over that time period, which is kind of relevant because when you think about it, the last 10,000 years or so is when human civilization is established, when humans started collecting together in towns, agriculture developed and all of that. Over that time period, the temperature has never been as warm as it is now, nor has it changed as quickly as it's changing now. And that's really important information because it allows us to look again at the physics of what we're seeing, of the greenhouse gases and that, and say, right, well, we know what we're seeing, we know why we're seeing it, and we can then start to predict where we're headed under various scenarios of emissions, for example.
Okay, so let me ask you then, are we seeing in the ice cores any changes in the climate, the atmosphere, the environment, et cetera, that would be beyond what we would consider natural variance?
It's a very good question. One of the things that's worth remembering straight up is that Antarctica is kind of odd place in the sense that it's a continent right at the bottom of the planet, surrounded by an ocean. And so one of the things that we know even from thermometers and our measurements today is that, it's good news actually, Antarctica is warming but more slowly than the rest of the planet because it's got this natural kind of air conditioning of the winds and oceans around it. The exception here is that the ocean itself is warming, and where it touches the ice, that's having a significant impact and melting the fringing ice around the edges. But we're not seeing large changes across the centre of Antarctica yet, and that's because it's so cold and isolated. But the ice cores show us a range of really interesting things. They show us, for example, I said there were sea salts, tell us about winter winds. We can see that in recent times, the winds that go around Antarctica have got stronger as the rest of the planet warms. And we understand why this is, that the pressure around Antarctica is shrinking, or the atmospheric pressure is shrinking into a tighter band of wind around the continent. And that's affecting things like rainfall in the southern hemisphere because that's taking storm tracks that used to hit, for example, Tasmania, where I live, or southern Australia, or in fact South Africa and South America. That wind belt has contracted towards Antarctica. And we can see the signature of that in the ice cores. And that contraction, the storm tracks are leading to drier climates, places like southern West Australia and parts of South Africa in particular. So I guess getting back to your question is, what are we seeing on the really short time scale? It's difficult to see things other than the kind of examples I'm telling you about, shifting winds and that sort of thing. The real power of ice cores, I think, from Antarctica has been to tell us the big picture of what's happening in the longer term. And the biggest contribution so far, I think, to past climate comes from the deep ice cores in central Antarctica, which have unfurled before us the history of the planet's temperature and what greenhouse gases, particularly CO2, have done through that time. And it's remarkable. If you look at the last 800,000 years, which is the longest ice core record we have at the moment, you see a record where temperature goes up into warm periods like we've currently got at the moment. The Earth's temperature at the moment, even before we started interfering with greenhouse gases, was in a stable warm period that we call the Holocene, the last 10,000 years or so. Before that, there was a 90,000 year period of cold climate, which we call a glacial period. That lasted, as I said, 90,000 years, and the whole temperature of the planet was probably about 4 or 5 degrees colder than it is now. Doesn't sound like much, but it was enough to cause ice sheets across North America and Northern Europe, which were several kilometres thick. So northern New York State would have been covered by a 3-kilometre thick ice sheet, and yet the whole planet was only about 5 degrees colder at most. And so we see this fantastic pattern when we go back through the 800,000 years of cold ice ages and warm periods like we have now. Cold ice age, warm, and they happen about every 100,000 years. And the really amazing thing is that when you take the temperature from the ice cores and you look at the CO2, and you can see the two curves just fit on top of each other like they're being traced together. You can almost not see a difference. And what that tells us is that the natural cycle of our planet has carbon dioxide and global temperature in lockstep. And so the really key thing for that is that since the 1800s, 1900s, the CO2 has departed from that pattern, is going up at a very rapid rate, and the global temperature is being driven by the increase in CO2. And I think that, to me, is the biggest insight from ice cores, the coupling of the planetary CO2 and temperature.
Okay, so the less CO2 in the atmosphere, the colder the planet gets. The more CO2 in the atmosphere, the warmer the planet gets. So then to stop climate change, we just need to emit less CO2. How has no one thought of this? Anyways, it looks like we know what the planet might have looked like 5 degrees cooler, ice sheets over North America, etc. But has the climate ever been much warmer than it is today? Do we know what the world would look like then?
Sure. I mean, if you go back into deep geological time, and I'm talking now many millions of years ago, there were other drivers of climate that basically forced CO2 to be at higher levels. You've actually got to go back probably at least 3 million years to get CO2 at the level it is now. And at that point in time, the planet would have been several degrees warmer than it is now. And importantly, there would have been about 15 metres more sea level, because we would have had very little ice in Antarctica and very little in Greenland, if any. And so it tells us in the past that, yes, we've had warmer periods, but with sea levels 15 metres higher than present, it's not the world we're used to at the moment. So naturally, absolutely, go back far enough, the planet was warmer, but certainly the planet the humans evolved in and have developed our society for, it hasn't been warmer than it is today. And in fact, it has never been as warm, let's say, in the last 100,000 years.
Okay, I don't know if this is about to be the smartest question I've ever had, but when the warmer temperatures sort of come and go through this cycle and the ice melts as a result, does that cause any gaps in the ice core record because of that? As in the data from the warmer season melted away when it was warm? Or is there a way to see what was still going on?
You know, it's a really good question. And so, I mean, one of the benefits of having ice cores from right in the centre of Antarctica, where the ice is, 3 and 4 kilometres thick, is that you can be pretty confident that there was ice there for the last 1,000,000 years, 2,000,000 years. We got other clues about past climate, and a really good one on those long time scales comes from ocean sediments. A whole bunch of stuff in the ocean sediments tells us about past temperature, particularly the calcium carbonate in the shells of plankton that fall out in the bottom, and we can figure out from, again, the isotopes of oxygen what the temperature would have been of the planet. So that helps us with the ice cores. But back to your question, if you've got an ice core that comes from an area that's near the coast or part of West Antarctica, which we think is pretty vulnerable to melting away, you actually don't know whether you've got a gap that was driven by no ice. And a really good example is an ice core drilled in West Antarctic called the Waste Divide ice core. It goes back, I think, from top of my head, sort of about 80,000 years. And it raises the question is, why didn't it go back further? Is it because last warm period there wasn't ice in that part of West Antarctica? And that particular scientific question is one that's burning in the ice core community at the moment. There's an ice core that the British team led being drilled in a place on the coast of West Antarctica called Skytrade Rise, and that will see, I think, whether there was some ice in parts of West Antarctica in the last warm period 110 or 20,000 years ago. And there are plans for the US to drill an ice core that again would be sensitive to the collapse of West Antarctica and tell us more. There's a lot of really important questions like that about how the planet rearranged itself in the past. And I guess the really big one that we're looking at the moment is that we need and want to understand some big climate rearrangements that occurred around 1 million years ago. Now, I said the oldest ice core we have at the moment is 800,000 years, but we think there's places in Antarctica where we can reach a bit older than that. And so both the Europeans and our Australian ice coring program and the Japanese are all looking at, and Chinese drilling for this 1 million year old ice. Actually, it would be nice to get to about 1.5 million years. The European team is kind of winning the race at the moment. They've got an ice core project well underway. They've got down to probably several 100,000 years, and perhaps this coming summer in Antarctica they might reach the bottom, and we'll find out whether they get 1 million year old ice. But there's an Australian program where we want to try and replicate that, test it. And as I say, Japan, China, Korea and the US are also thinking of drilling very deep old ice cores. But it's an exciting project.
Can you tell us a bit more about this project?
This is the what we call the Oldest Ice Challenge, or the 1 million year ice core project. And so the reason it's important is that I've mentioned how the ice age cycles come and go every 100,000 years. The ocean sediment cores tell us that actually at about 800,000 years ago, that pattern was disrupted. And if you go back to 1 million years and earlier, the cycles were more like every 40,000 years. And so that poses an interesting question of, if the oldest glacial cycles were 40,000 years long, what changed in the climate system to then produce 100,000 year long cycles for the last 800,000 years? And very frustratingly, as I said, the oldest ice core we've got just cuts out at that 800,000 year mark. So if we can get an ice core that goes to 1 million, or preferably at 1.5 million years, we can then start to determine what it is in the climate system that changed. Was it CO2 levels in the background? Some theories suggest that it was also to do with the way ice ages scoured the bedrock under the Northern Hemisphere ice sheets of America and Europe. These are questions we don't know the answer to, but hopefully by getting that deep oldest ice core, we can answer them.
Okay, so let's say we were not limited by human technology. Do we know how old the very oldest or deepest or most difficult to reach ice core would be?
Not well, and so that's part of the challenge. There's been a long, probably a decade or more long project of flying radar over Antarctica for a range of reasons, but to map it out and doing modelling of how ice flows, which we can do reasonably well, to try and simulate what the age might be at the bottom of Antarctica. And so the best guess we have is that there are some of the places that we're currently drilling where the ice might get to 1.5 million, maybe 2 million years in a continuous sequence. And that's important because if you want to get the best record possible, you want to actually have a nice, continuous, uninterrupted record. I should point out that there are places in Antarctica where we've already recovered ice that's well over 1 million. In fact, there is some ice that's 2, 3 and 4 million years old. It didn't come up in a nice continuous sequence. It's ice that was actually trapped in regions that became nearly stagnant and has become pushed up against mountains. And so if you drill into that ice that's actually being pushed up, you can sometimes get some stagnant areas of old ice that have got, these very old ages. So again, the record looks like at the moment being perhaps 4-ish million years, maybe 5 million years for the stagnant ice, and 1.5 to 2 million years, if we're lucky, for the continuous.
Wow. Well, you let me know when we reach that 1.5 million mark, and we'll have you come back on the podcast to tell us what we learned. I'm going to circle around a little bit. We talked about the past. We alluded to the future. I want to learn more about what the ice cores can tell us what we need to be doing today. I came across a bit of research you did that discussed how information stored in the ice cores of Antarctica can inform decisions about drought management in Australia. Can you tell us how that could be, and maybe if you know of any areas where ice cores can inform current environmental mitigation measures?
That's a good question, because even though our computer models, climate models, are increasingly good and accurate, you always want to test them against something that you can observe. And the example that you're alluding to comes from some ice core work we did. There's a place on the coast of Antarctica called Law Dome. In fact, if you just draw a line south of Western Australia until you hit the coast, you come to this dome of ice that's attached to the coast that's about 100 kilometres across. The dome is about 1.2 kilometres thick, and it's kind of a really special place because it's so near the ocean. It gets high snowfall and records ice records that are really detailed. And so what we did is we looked at the Law Dome ice core, and we could actually very easily detect the thickness of the snowfall layers every year for the last 2,000 years. And we found that the thickness of the ice layers for the last 30 to 50 years, since about 1970, was thicker than normal. We thought, what's going on? We'd accounted for the fact that the ice gets compressed, right? So we'd worked out how to take that effect out. But why was there more snowfall since about 1970 at this place called Law Dome? And so we then started to look at what was happening with the meteorology, because we had nice satellite data and winds. We found out that what was happening was when we got high snowfall at Law Dome, we were getting moist air coming down from Australia and delivering snowstorms. Kind of makes sense. Lots of moist air, more snowfall. But the really interesting thing we noticed was that part of that same circulation was bringing relatively cool, dry air back up to Western Australia. And that cool, dry air was shutting out the major winter rainfall that fed the wheat belt in that region. So it turned out that we'd found a link between climate in two places that are thousands of kilometres apart. And so high snowfall in Law Dome meant low rainfall in Western Australia and vice versa. And so that was very useful because farmers and policymakers had been looking at the issue of the drought in Western Australia. Like, they didn't need us to tell us about that. They knew it had been dry since 1970. The question was, is this something that's just part of a natural cycle and it's going to get better and we'll get back to being able to rely on the wheat belt for what was normal cropping? And you can't answer that easily if your weather records only go back 100 years. But what we had now was a linked ice core record that went back 2,000 years. And what we're able to find is that in that 2,000-year period, what's happened since 1970 is really unusual and doesn't look like it's part of the natural pattern. And so, on balance, the ice core is starting to tell us that policymakers and farmers should be expecting that this is not normal, it's not going to come back to normal, there's something driving it. And so you put that then with the computer model of the climate, and we've done this work as well, and you start to actually be able to tell, is the circulation unusual from the modelling point of view? And it is.
Wow. So that's just one example, I guess, one case study, right? But it speaks to how this sort of data and coupling these two databases together can be used to adaptation, I guess, across the world for probably a number of different challenges. One question that I keep hearing getting asked with the climate or with weather events is this a pattern or is this an anomaly? And we know that there are some anomalies that are becoming a pattern that are prompted by human emissions. But I know that there are some long-term climate cycles that happen, on scales long before humans were around, ice ages and such. Is it a simple question to ask you what drives those cycles?
It's not simple. I mean, I think one of the big unanswered questions in ice core and paleoscience generally is that we kind of know to first approximation why ice ages happen, why they come and go. And there was a Serbian scientist called Milutin Milankovic. Milankovic came up with this theory that said actually, because the Earth's tilt changes over time slowly, and because the Earth's orbit changes its circularity slightly, sometimes it's a bit more oval, sometimes it's a bit more circular, and also that not only does the tilt change, but the Earth is spinning like a top slowly. It's about every 20,000 years to repeat that cycle. And so if you put these known cycles together, you can kind of say, when is it that summers in, say, Northern Europe are mild and quite cool? And it turns out that there are periods about every 100,000 years when summers get cool enough that snow that's been there since the previous winter doesn't completely melt. And that's the condition you need to start an ice age, because that means next year's snow builds up on last year's snow, and before you know where you are, you build the big northern hemisphere ice sheets that are, as I said, 3 kilometres thick over New York State or Switzerland. And so that's Milankovic's work, and it's really good and it's really cool. And we kind of know that that's a part of the explanation, but by itself, it's not enough. And you scratch your head and think, what is it that's actually joining in this dance that's helping to get you into an ice age or back out again? And not surprisingly, it's the CO2. That's why the ice core CO2 record tracks the temperature so closely, because one influences the other. And in fact, it's a two-way influence. And so if we can understand those processes, this is not just abstract curiosity. This is information that helps us say, what's going to be like in Boston in 200 years' time? And you think, who cares? I'll be dead. But if you look back, there was development and ports and people living in Boston 200 years ago. It's not that long. And so actually, we need to care about what the planet's going to be like in many generations from now.
Well, that's a little bit scary, but I'm glad we're at least going to be able to know what's coming towards us. And all the more reason to listen to the scientists, right? Because it seems like we have a very solid foundation for our projections and very solid evidence for the CO2 temperature connection. So yeah, I guess we just have some work to do. As we start to round out the conversation, I want to ask you, is there anything that we missed today? Anything that we didn't talk about that you think is important to mention in this discussion about ice cores?
I always like to tell people that, sure, 2 degrees of warming is not great. It's not as good as 1.5, but it's a lot better than 2.5 degrees. And so every 1/10 of a degree that we can strive to actually knock off the actual ultimate rise is a win.
I think that is a perfect note to end on. Well, then my last question is, where can people find you and follow your work?
You can find me on X, Twitter, whatever, as @TasVO. Also on Blue Sky, same handle. And you can also follow the Australian Antarctic program. That's AusAntarctic on various formats. And you'll be able to see what we're doing.
Okay, perfect. I will put those in the episode description. And this is the part where I say thank you so much for taking the time to talk to me today. Thank you for teaching us all about ice cores. And perhaps most importantly, thank you so much for your important research in this space.
Thanks, Clark.
You've been listening to South Pole. You can find more information about this week's guest and links to their work in the episode description. Cover art for the show was done by Laurel Wong, and the music you're listening to was done by Neela Ruiz. I am your host, Clark Marchese, and this episode was produced and engineered by me. And if you found it interesting, send it to someone you know. South Pole is part of a larger network of sciencey podcasts called Pine Forest Media. We've got one on plastic, one on drinking water, and a couple of new ones coming out soon. You can find more information about us in the episode description as well, or on our website at pineforestpods.com. We're also on Instagram and TikTok at Pine Forest Media, and if you love the show and you want to support science communication like this, a 5-star rating across platforms and a review on Apple Podcasts is one of the best things you can do to help science reach more people and for the entire network to grow. All right, thank you to all of you who have made it this far, and we'll talk soon.